Hello everyone and welcome to part 4 of this week's lecture. In this lecture we are going to look at development of different formulations for velocity profile for fully developed laminar flow. In previous parts we looked at the velocity profiles and I showed you these diagrams that for the case of laminar flow we have a more parabolic velocity profile, and for the case of turbulent flow we have a more flattened velocity profile, and I said that these velocity profiles are actually a direct consequence of viscosity, because if we deal with ideal fluids it means that there is no viscosity between the layers or no friction between the layers. We get a more straight or a flattened velocity profile that is not realistic. So it means that to calculate the actual flow rate through a pipe, we need to develop these velocity profiles. So let's look into the math that we need to develop these velocity profiles. So we can develop velocity profiles analytically by solving equations for laminar flow where the Reynolds number is less than 2100. There is a mistake here, it should be 2100 here. Where the velocities are low, and it means that the fluids move in a straight line or in straight channels, and that make our life quite easy mathematically because we can solve these equations then analytically. While for the case of turbulent flow, because of the high Reynolds number, velocities are very high and it generates a lot of irregular velocity components, and as such we cannot solve these equations mathematically. Okay, so we have to rely on experimental measures to develop different relations. And as Richard Feynman said, that turbulence is the most important unsolved problem of classical physics, and even despite being in 21st century, we cannot solve turbulence by using analytical equations. Okay. So what is a fully developed flow? So when a fluid element enters the pipe, for example, it has a uniform velocity profile. It means that all the layers are more or less at the same velocity. But as the fluid enters this empty pipe, it starts to develop a velocity profile, because at the wall here, the velocity will be 0. And as it goes towards the center, the velocity becomes higher and it's developing a velocity profile now. And after a certain length, the velocity profile stops changing anymore. It means that the velocity profile has fully developed, and even if the pipe is 10 meters long or 100 meters long, this velocity profile is not going to change unless there is a change in the direction of the pipe, or you put a fitting that actually creates turbulence, and then you have to wait again for the certain length for the velocity profile to develop again. Okay. So this length that of the length of the pipe that takes for the velocity profile to fully develop is what we call uh, entrance length. Okay, and from experiment observations we know that these entrance length, the ratio of entrances over diameter is equal to 0.06 Reynolds number, and for the case of turbulent flow, the Reynolds number, this is the relation here. And if you put the values of Reynolds number in these two equations, you will see that the entrance length for turbulent flow is much shorter compared to the entrance length of laminar flow. So please try to put the values of Reynolds number and look at the effect of this entrance length. So for the development of velocity profile, we are going to follow three main steps. Step one is that we have to perform a force balance where we relate torque with the driving force, and that driving force can be the gravity or it can be the pressure force. Second step is that we write tau in the form of velocity gradient using constitutive equations. It can be a simple equation like this Newton's law of viscosity, or it can be more complicated equations that relate tau with velocity gradient. And number three is that we are going to perform integration, and then we are going to apply the boundary conditions to find the constant of integration. Okay, so let's look into that. So for this case, we are going to look at laminar flow in a pipe, And so let's consider that you have a pipe of diameter r, and the fluid is flowing in the direction x as it is shown here, and the r component is perpendicular to the direction of the flow. Okay, so this is the radial direction. And we have this fluid element again, just using the similar method that we use for hydrostatic pressure calculation. We are using a similar method here. We are assuming a differential cylindrical element of fluid, and on this side of the element we have a pressure P, and on the other side here we have a pressure P plus partial P, and the fluid is moving at a velocity u. So if the fluid is at equilibrium, it means that all the forces on this fluid element should be zero, and the fluid is moving because we are applying pressure force, and we have an equal opposite force that is due to the viscous forces. It means that the shear between the layer, or the friction between the layers, wants to stop the fluid, while the pressure is the force that wants to move the fluid. Okay, so if the system is at equilibrium, these two forces should be equal. Okay, we can write that pressure, because it's a force balance, so we have to write pressure times area, because we know that pressure is force per unit area, and actually force is pressure times area. So we can write P times pi r squared, that is the cross-sectional area, minus P plus partial P times area, that is the area on this side, and then that should be equal to the viscous force. So viscous force we know is the shear stress times area. And one important thing to notice here, that here we are multiplying shear stress with the tangential area. Okay, so pi r square is the cross-sectional area, but pi r 2 pi r partial x is actually the surface area of the cylinder, that is the circumference, that is 2 pi r times the length of the cylinder. So please remember that these two areas are different. Okay, this is the normal area, or the force is acting on this area normally, while this shear stress is acting on this tangential area. We can further simplify this equation. We can cancel out the P term here, and if you rearrange this equation in the form of shear stress, we can write it as shear stress is equal to minus r by 2 partial P or partial x, and here there is a mistake here. It should be partial derivative, because this equation is a form of partial derivative, but we know that there is no flow in r direction or theta direction, so we can actually make them zero, and as such P only depends on x. And if this is the situation, we can write this partial derivative in the form of ordinary derivatives. Okay, so on your blackboard in this lecture's folder, I have put additional notes on different coordinate systems and how we can actually represent different components and different derivatives, for example. So please have a look at it to understand this lecture in a better way. So now we have the relation of tau in terms of the driving force, that is delta P over X, pressure drop per unit length. The second step is now we need to write this tau in the form of velocity gradient from a constitutive equation. So we are using here the Newton's viscosity law of viscosity. And if you put the value of tau in this equation, we can write it like this. That is the velocity gradient with respect to r, that is the radial direction, because when we talk about velocity, Newton's law of viscosity, we talk about velocity gradient in y direction that was perpendicular to the flow, and here r is the direction that is perpendicular flow. So that's why we write du over dr equal to r over 2 mu dp over dx. Okay, so step 3 is now to integrate this equation, and so we are going to now integrate, and after, it's a very simple integration. So on this side we will get u, that is the velocity of the fluid, equal to dp over dx r square over 4 mu plus c, and c is the constant of integral, because it is an indefinite integral, so we have this constant of integration. Okay, So by applying the boundary condition, we can calculate this value of C. So we know from our system that when R is equal to capital R, it means that you are at the wall. And we know that at wall, the velocity is 0 because of the non-slip conditions. So we can write, if we put the value of R, small r as capital R, and we put the value of U as 0, we can calculate the value of C from this equation here. Okay, so that is this given here. And if you put back the value of C now into this equation, we get bottom equation here, that is that the velocity is equal to minus 1 over 4 mu dp over dx, capital R square minus lowercase r square, that is the any arbitrary radius, and that is the radius of the channel. It means that that is the r that is here, for example, at the wall. So if you put the values of different r's and develop a velocity profile, you will see that you get this parabolic velocity profile. Okay, so this is how we can develop a velocity profile for this, for example, for the laminar flow. Now we have, okay, so we have the velocity profile, but what we are really interested in is the flow rate, because that's what we need to, for example, in calculations and also in quantity of the fluid. So we need how much fluid is transferred per unit time. And so to solve that, we need to calculate the flow rate. Okay, so for example, let's look at now that you have an annulus of fluid. In a way, again, we are assuming that this dark blue is the fluid, and this outer edge is the wall of the pipe, and the fluid has a radius r, and the differential radius or the thickness of this element is dr. So the flow rate of this differential element would be dq, or partial q, equal to u, that is the velocity times area. Okay, so if you do the unit check, so u is meter per second, area is meter square, so you get meter cube per second, that is the flow rate per unit time. And we can develop the expression for partial area or differential area. Here we know that the area of the outer area of this this annulus is pi times r plus partial r square minus the area of this inner circle, that is pi r square. Okay, so that is the differential area of this blue element. And if you simplify this equation and write, you have the partial a is equal to 2 pi r partial r plus pi times partial r square. Ignore this partial r term here, and by doing that, we also see that the a is now only a function of r, so we can convert this partial derivative into ordinary derivative here. Okay, so we have the differential area. We can feed into this equation. We know the velocity from our previous calculation, that u is given by this relation here. We have dA from the last slide. So if you just feed the values, you get the expression for dq, and it means that we need to integrate on both sides. So if you do the integration, we have dq, the integral of dq is q, and if you integrate it from 0 to r, because we have to consider the whole radius of the channel, because the fluid is present from in the whole radius, so we have 0 to capital R, that is the radius of the pipe. We can write it as here, for example, we multiply this r inside, we cancel out 2, and we have 4 and 2 here, so we have 2 in the denominator. And if you do the integration of this equation, you get this equation here. Okay, and so this equation, if you now put the value of r and 0, so after simplification, we get that q is equal to minus pi r raised to the power 4 over 8 mu dp over dx. Okay, so this equation is the equation to calculate the flow rate of a flow through a pipe. Okay, And this equation is called Hagen-Poiseuille equation, okay, a French scientist. And what it states that the flow rate is only possible if you apply a pressure difference. Okay, if there is no pressure difference, there is no flow. Okay, and another important thing to notice is that the flow rate is actually dependent on the geometry of the system, and it also depends on the viscosity of the system. Okay, so there are three parameters this flow rate depends on: the geometry of the system, viscosity of the system, and the pressure drop. Okay, so okay, we have the equation for flow rate, so we can calculate now the average velocity. So average velocity should be the total flow rate divided by the total cross-sectional area. So we have from this previous equation, we know the value of Q, we know the value of area, that is pi r square, so we get the expression for average velocity. Okay, so if the layers are moving in different speed, so if you average them, all these velocity of these elements, you get this term here. Okay, and because we know that there is also a maximum velocity, and maximum velocity is at the center of this channel where the friction effects are the least, or the wall effect on this velocity of this central layer is negligible. So we can write that u is equal to we know the equation of u from this equation, and at the center we have this r lowercase r value becomes 0 because that's the center. So if you just cancel this out, you get this expression of maximum velocity. And if you compare u max with this or the average velocity, you will see that the maximum velocity is actually 2 times of the average velocity. And as you can see here, that is why you have a parabolic velocity profile. Okay. So we can also write this equation, that is Hagen-Poiseuille equation, instead of radius, we can write it in form of diameter as well. So if you just replace r d over 2, okay, so if you replace that, we can just convert this equation from r to d. And also we can write it in the form of pressure drop per unit length, that is delta p over L. So it means that if you travel, for example, a certain length of the pipe, what would be the pressure drop? Okay, because the pressure is going to drop because of the friction between the layers. Okay, so if you again integrate both sides, and you take, for example, dx on this side and dp leave on this side, so integrate in the form of channel length and the delta p, so we can write q is equal to minus pi d to the power 4 over 128 mu L delta P. Okay. And again, it shows that the Q is only possible if you have a pressure gradient. Okay. And the pressure is going to drop for a certain value of Q. So that is the final Hagen-Poiseuille equation in the form of diameter. So what it means, the flow will only be possible if you have a pressure drop. And if you have a flow, it means that you are going to have a pressure drop. Okay. So to obtain a particular flow, you need a certain pressure driving force to overcome the losses to pressure that occur. Okay, and this pressure drop occurs because of the resistance of the flow due to viscosity. Okay, so this is the consequence of viscosity on the flow rate of the system. And this is very similar to for example, Ohm's law in electricity. This is now a self task for you guys, so try to develop the velocity profile of flow between two parallel plates, and all the conditions and the details are given here on this slide. You have a steady state flow, you have a laminar flow, and you can ignore the gravity effect. So try to do the same analysis like we did for the flow in a pipe geometry. and see if you can get to these solutions following the same method that we did for a pipe flow. Okay.